could an ancient meteorite impact have been a pivotal force in shaping the evolution of life on Earth? A recent investigation has redefined the timeline of a significant meteor strike in Scotland, shifting its impact date from the widely accepted 1.2 billion years ago to approximately 990 million years ago. This one adjustment significantly alters our understanding of Earth's history and invites a fresh perspective on when more complex organisms began to emerge from the oceans and inhabit land. The crux of this groundbreaking study lies within a particular segment of rock known as the Stack Member, located in the rugged terrain of northwest Scotland. Within this geological treasure trove, scientists have uncovered tiny crystals that serve as remarkable chronometers, meticulously capturing the moment of the meteorite's collision with Earth. Why does the Scottish impact hold such significance? Under the leadership of Chris Kirkland from Curtin University, along with a team that included experts from institutions like NASA's Johnson Space Center, this research blends detailed field analysis with sophisticated laboratory techniques to construct a coherent timeline of events. According to Professor Kirkland, these microscopic crystals recorded the exact moment of impact, with some transforming into a rare mineral known as reidite. This physical evidence transcends speculation, providing a clear temporal anchor for the meteorite collision. Currently, many of the Earth's known impact craters lack precise dating, which hinders our understanding of the interplay between life and climatic conditions. A review conducted in 2022 identified 188 craters around the globe, yet only 37 were associated with exact dates. This research adds one more crucial timestamp, connecting the meteorite strike to a time when life was undergoing rapid transformations on land. The geological witnesses of the impact. At the core of the findings is zircon, a resilient mineral known for its resistance to heat, erosion, and chemical breakdown. When zircon crystals form, they can capture uranium atoms, which subsequently decay into lead over time, providing a reliable method for dating. This process is often referred to as UPB dating. An additional element of interest is reidite, a form of zircon that is produced only under conditions of extreme pressure during violent impacts. Past studies on the Stack Member have revealed instances of reidite preserved in shocked zircon, serving as evidence of the intense pressures present during the meteorite collision. The Stack Member itself is comprised of ejecta, a mixture of fragmented rock, tiny spheres, and altered melt deposits that rain down to Earth following the impact. Its texture reveals signs of reshaping by water and gravity, which complicates the aging process. However, this also preserves a rich history of subsequent events. Understanding the timing of rock formation, the research team specifically focused on shocked zircon and its recrystallized zones, areas that form due to heat post-impact. These zones offer the clearest insight into the last time the zircon clock reset. By analyzing disturbed and undisturbed zircon from layers above and below the ejecta, they aim to ascertain whether the reset signal was particular to the impact event and not due to subsequent geological processes. Professor Kirkland noted, when a meteorite strikes, it partially resets the atomic clocks inside the zircon crystals. Utilizing this partial reset, the team was able to isolate the precise moment of impact. The findings pushed the Stack event into the early Neoproterozoic era, a significant time characterized by evolving continents, atmospheric changes, and the emergence of complex multicellular organisms venturing into new habitats. What does this shift in timing imply? Previously, minerals discovered in the same geological unit were dated to around 1,177 million years ago, which became the common reference point. However, the new results, based on zircon evidence, suggest a more recent episode. This hints that earlier dating may have relied on sediment that was either altered or contained detrital minerals rather than genuine impact products. Importantly, The newfound dating parallels the existence of early freshwater eukaryotes identified in nearby rocks. These complex cells, which encompass plants, animals, and fungi, showcase evidence of life's expansion beyond aquatic environments around the same time as the meteor impact. While this correlation does not imply a direct cause and effect relationship, it certainly opens up avenues for exploration, inviting further questions about how such cataclysmic events could have reshaped lakes, soils, and atmospheric conditions, consequently influencing early ecosystems. As of now, researchers have yet to definitively identify the crater responsible for creating the Stakfata ejecta. Although impact signatures are clear, the source is still a mystery. Ongoing geophysical surveys, meticulous mapping, and smart sampling strategies could refine the search. With improved dating, scientists are better equipped to pinpoint which types of rocks are viable candidates for hosting the crater. Beyond Scotland, the broader implications. Accurate dating of meteor impacts allows scientists to examine their connections to the biological and environmental developments on the planet without falling prey to ambiguity. With established timelines, researchers can investigate whether notable shifts in sediment, chemical composition, or fossil records are correlated with impact events. This understanding holds immense importance in narratives surrounding the evolution of complex lifeforms on land. Existing fossil records suggest that diverse species of eukaryotes were thriving in freshwater and terrestrial ecosystems around 1 billion years ago, now coinciding neatly with the timeline established by the Scottish Impact Study. In addition to shedding light on biological developments, unearthing the precise timing of these impacts also enriches our comprehension of how planetary systems recover after significant disturbances. Insights gained from this research could benefit everything from climate modeling to long-term assessments of Earth's habitability. Research teams can now go back to local fossil-bearing formations with sharper inquiries regarding community structures, nutrient cycles, and environmental stresses. Laboratory groups might also explore how shock and heat affect zircon in controlled settings, fine-tuning their methods for future investigations. As the quest to locate the crater continues, armed with enhanced tools and a more precise timeline, researchers are optimistic that clarity will emerge from a once gloomy chapter of our planet's deep history. This exciting study can be found published in the journal Geology.